Hello everyone, I'm Carlos Duarte. I'm a staff researcher at CBE, and today I'm excited to present to you a new project funded by the California Energy Commission to investigate heat pumps using ultra-low global warming potential refrigerants plus thermal storage for residential buildings. So water heating and space heating are the two largest energy end uses across California homes, making up roughly 38 and 22% respectively of annual household energy use. Since these loads are still being served by natural gas appliances, natural gas remains the main fuel used in homes, as you can determine from this donut chart, the outer ring of it. And these natural gas appliances are simple to operate and relatively inexpensive to purchase. However, they produce direct on-site greenhouse gas emissions that worsen indoor and outdoor air quality. And they also lock in homeowners to fossil fuel price fluctuations. And most importantly, they do not align with California's decarbonization goals, which aims to transition to a clean energy grid by 2045. So this research aims to provide homeowners with more options to cost-effectively electrify their space and water heating end uses, while recognizing that the grid is still transitioning to clean energy, where intermittent renewables significantly affect pricing in grid carbon emissions. Through this grant, we plan to develop and assess ultra-low global warming potential, or GWP, multifunction heat pump with thermal energy storage for residential use. It's going to involve product development, laboratory testing, field demonstration, and whole building energy simulation. It's a 4-year, $2.5 million grant provided by the CEC, and also match funding through PG&E, MIDEA, RAHAL, and the CBE Industry Consortium. So this is the match funding that Gail was talking at the beginning of this meeting. So before I start showing you the proposed system, let me show you what a conventional residential mechanical systems look like. And you might be familiar with this equipment in your own home. So a typical home in California has a gas-fired furnace for space heating, a gas-fired water heater for hot water, and if you live in hot weather, you most likely also have an air conditioning unit, usually a split system where the condenser is on the outside and an evaporative coil inside the home, inside the air handling unit. So there's going to be natural gas lines running to the gas-fired water heater and furnace, and you can also have a refrigerant line running into your home. And the refrigerant in these lines and this equipment have a GWP of over 2,000, and any new retrofits and new equipment installs after 2025, they should have refrigerants of 700 or less. These global warming potentials are relatively high that any leakage or improper disposal of the refrigerants at the equipment's end of life can undermine any climate benefits that we gain from improving the equipment's efficiency. So how do we improve upon this? So to improve it, we are partnering up with Harvest Thermal, a local clean energy technology company that provides smart, efficient solutions for space heating, cooling, and hot water. Harvest Thermal is going to lead our product development task, and they're going to leverage their existing system platform to integrate an ultra-low global warming potential heat pump with thermal energy storage. And to electrify water and space heating in households, they have developed a system that you see here that consists of a CO2 heat pump, thermal energy storage, and a smart controller. The system can easily integrate with a homeowner's existing air handling unit, and it's also flexible enough to do space, multi-zone space conditioning by using fan coil units or radiant terminals. Their smart controller optimizes thermal energy storage to target low price electricity or low carbon emissions. So they are able to remove the gas-fired appliances with this ultra-low GWP heat pump that has a GWP of just 1 because it's using CO2, which is the reference refrigerant. However, there's still room for improvement. First, we still need to get rid of the higher GWP air conditioning unit that you see on top. And second, CO2, the device itself is relatively expensive and operates at high pressure point, which requires specialized training to install and maintain. So how do we improve upon this electrification solution? So we improve it by replacing the CO2 heat pump with a lower cost heat pump based on an R290 refrigerant. In doing this, we can also provide cooling, eliminating the additional air conditioning unit and the refrigerant lines running into the house, which can sometimes raise safety and health concerns when using the lower GWP refrigerants. So now we have a multifunction system that addresses the major end uses in a household, and it also reduces the likelihood that an electrical panel upgrade is required because we're electrifying these major end uses with just one single appliance that's serving these multiple services. The GWP in this particular unit is less than 1, so it seems like a good system or good design, but like the main concern with R290 is that it's also known as propane, which is a highly flammable refrigerant. But the reason it's highly desirable to be used within HVAC equipment is that it has a very low global warming potential, like I already discussed. And the propane's properties also allow heat pump units to produce hot water at higher efficiencies and at higher water temperatures compared with leading alternatives, including CO2 heat pumps. But to mitigate all these risks associated with using propane as a refrigerant, the outdoor unit is installed on the outside, as you can see here, with no refrigerant lines running into the indoors. Water lines are used to distribute all that energy inside a home, like I showed you in the previous slides. So all the propane is contained with this monoblock, and furthermore, the refrigerant is factory charged and sealed, so HVAC technicians don't have to charge the unit in the field. And it only uses a small amount of propane, which can largely be contained within 2 small camping canisters. Many of us probably have stored 20-pound propane tanks used for grilling in our car garages. So nonetheless, as part of this grant, we need to validate its safety, performance, grid value, and the feasibility to retrofit these kinds of systems into the California housing stock. And to conduct this evaluation, we begin with a laboratory testing in PG&E's Advanced Technology Campus location, located in San Ramon, California. And this PG&E lab is being upgraded to handle A3 highly flammable refrigerants. We will test whether the system can reliably deliver space heating, cooling, and hot water efficiently under California conditions, while also responding to California's grid requirements. We're also going to measure how well the thermal energy storage system can shift load, reduce peak demand and emissions, and also maintain performance. Then we're going to do a pre-demonstration at UC Berkeley's Richmond Field Station. The Richmond Field Station is well suited for this type of pre-demonstration because it is home to a variety of research centers that often build prototypes that have specialized safety needs. For example, researchers are building rocket-fueled rockets, hydrogen fuel cells, and so the regulatory barriers to install this type of system in a building are greatly reduced. So this field test moves beyond the laboratory by evaluating the system over a longer period of time in a realistic building environment. And it also gives our project team a flexible space to refine controls and system design and generate real-world performance data and practical guidance for the broader retrofit deployment of these types of systems. Then we're going to apply the lessons learned from the Richmond Field Station into a deployment in a Berkeley home to show that it can be installed safely, permitted, and operated in compliance with local regulations. This is going to require working closely with the city of Berkeley to address any safety concerns posed by propane's high flammability. And this field demonstration also helps validate retrofit performance, comfort, peak load shifting in practice, while also generating additional lessons learned, data, and provide training materials that we can use for a broader adoption. So we also have a data-driven analysis task, where we're going to combine our measured and public data to build a building energy simulation models to evaluate how the proposed system will perform across California homes, climates, and utility rate structures. We'll also be comparing this proposed system against common alternatives and also leading alternatives like the CO2 heat pump that I discussed earlier. We also have a market transformation task that's going to focus on the non-technical barriers that often slow adoption, including permitting, workforce training, customer understanding. It's going to create practical tools, guidance, and public resources that can help homeowners, contractors, policymakers, and local agencies scale up our proposed system across California. And for this task, we are leveraging the expertise of a CBE member, Smith Group. They have deep expertise in decarbonization strategies and regulatory engagement, as well as direct involvement in national highly flammable refrigerant codes and standard efforts. And they also will be leading having interviews with authority having AHJs to identify any practical pathways for safe, code-compliant deployment of these proposed systems. Overall, the project hopes to lower household energy use and costs, shift electrical demand from peak periods, improve grid flexibility, and reduce carbon emissions from space and water heating end uses. So you can scan this QR code, which is going to take you to our project webpage, and we are going to keep it updated as this project progresses, which we expect to have a start date sometime soon, hopefully before the end of this semester. So thank you, and I'll take any questions that you might have.